Good evening. On behalf of Engineers Australia, I am delighted to welcome you to our Infrastructure Thought Leader series, Innovative Engineering and Design with Brick, the Smart Design Studio. My name is Greg Ewing from Engineers Australia. Firstly, on behalf of Engineers Australia, I'd like to pay our acknowledgements and respects to the traditional owners of the land and recognise their continuing connection to land, water and community. We repay our respects to their cultures and to their elders and leaders, past, present and emerging. I would now like to welcome our moderator for this evening, Brett Ward, General Manager, International Marketing at Brickworks Building Products.
Thank you, Greg, and good evening, ladies and gentlemen. On behalf of Brickworks, thank you for joining us for tonight's event. I'd like to thank William Smart of Smart Design Studio and Jonathan Lowe of Northrop for their time this evening. Brickworks Building Products is one of Australia's largest and most diverse building material manufacturers. Our company has built an enduring reputation with our clients based on innovation, professionalism and ever dependable products. Our portfolio includes some of Australia's most recognised brands, including Austral Bricks, Bauer Bricks, Bristol Roofing, Austral Masonry, Austral Precast and Urban Stone. We have the goal of making beautiful products that last forever, made locally with sustainable manufacturing a key focus. Now tonight's presentations will give you greater insight into an innovative, sustainable and sculptural project here in Sydney, which is both a place for work and a place to live. Smart Design Studio's new headquarters is an impressive example of what can be achieved through collaborative architectural and engineering design. But before we hear from our two guest speakers, we hope you enjoy this introduction to Smart Design Studio's new headquarters.
Hi, I'm William Smart. I'm the Creative Director of Smart Design Studio. We chose this location because we're very attracted to the conservation area that's just been named. And within this area, the council is seeking to preserve all the old warehouses that exist at the moment. The building here was originally a factory that made lollies, and we kept most of it. We kept 80% of the building, which we loved, and it's kind of our first principle of conservation, is to try and retain whatever we can, and then we built 20% as new. Innovation was very important to us, and we also understand that not all clients are people who want to invest in innovation. They want tried and tested solutions. So we sought innovation on sustainability, and we also saw it on structural design. And the shape is called a Catenary shape, and it's the same shape as holding a string. So if you were to hold a string, it will form an arc, and the arc is called a Catenary. If you flip it up the other way, so it goes upwards, the pressure that pushes out equalizes with the pressure that pushes down. So gravity is balanced in perfect harmony. And that means that the load of the brick is evenly distributed down to the ground. My favourite part is definitely our home. I love walking up the stairs and looking through the space at the end of the day. And just recently, I suppose due to the working from home scenario, we've been spending quite a bit of time here, and it's just beautiful to be in. The light tracks through the space in a beautiful way. It's very quiet. There's a kind of I find a joy to the shape of the room, and I think we've nailed so many aspects of it that I kind of sit here and feel like I'm in a very well tailored space.
I would now like to welcome and introduce our first guest speaker for this evening, William Smart. William Smart is founder and creative director of Smart Design Studio and is directly involved in every project, contributing at all stages from design to final delivery. William continually explores ideas in his work relating to flexibility, contemporary living, and the merging of art and architecture. His and the studio's approach to design is holistic, combining both architectural and interior design. William's enthusiasm and passionate attention to detail is fundamental to the studio's success, motivating a highly dedicated team of architects and interior designers to realise projects of high quality and innovation, producing work that is both detailed and resolved. Established in 1997 and with a staff of 40, Smart Design Studio is a multidisciplinary practice whose buildings have received critical acclaim and many prestigious awards, including the Institute of Architects Robin Boyd Award for Residential Architecture, the Institute of Architects Wilkinson Award for Residential Architecture, and the World Architecture Festival Inside Award for World's Best Residential Interior. Please welcome William Smart.
Hello, I'm William Smart from Smart Design Studio, and I'm here today to talk to you about our new studio in Alexandria, Stokes 14. I'd just like to start with a presentation. The building is located in Alexandria, which is halfway between Sydney City and the airport. It's a newly listed conservation area, which means that all these warehouses have to be preserved. We purchased a warehouse a bit like this, which was quite dilapidated. And from the inside, it's a beautiful old machine workshop where we really adored the light of the existing space. So we embarked on a project to renovate this building. We started by saying how much of the existing building can we conserve, which was about 80%, and that was our first sustainability move. The front part was demolished and we removed the asbestos roof and then built a new structure which encompasses the front 7 metres of the building, and then built above that a brick vaulted roof and then a new brick skin on the front face of the building, and then clad that with a metal roof sheeting and then multi-pane steel framed windows, a new highly insulated roof and 260 solar panels that makes enough energy plus more to run our studio. So together we have a cohesive building where the idea of the building is to form a new interpretation of an industrial warehouse building. I'll talk to you a little bit about the design of this project. We always start with sketches, trying to imagine the space, what is the atmosphere that we want to create, what are the opportunities, and we search for the architecture that we want to create. In many situations, this is designed from the inside out, which is our philosophy of design. So we make models as well as sketches, and these models are used to distill the ideas and to bring them to life in 3D. Through the course of a project, there are many, and they're often used to talk with the builders and other contractors about the ambition for the project. One significant part of the roof of the project is a catenary-shaped roof made out of brick, and the catenary shape is that which a chain forms when it falls. When you invert it, the chain will perform in the same way, so it's a perfect equilibrium where the compression of the bricks is transferred to the ground and it holds its form. We use this catenary shape in two forms, a large and a small vault, to bring light and to form the enclosure of the apartment over the top of the building. And to develop this in detail, we collaborated with UTS, who have experts in parametric modelling. So we developed the perfect prototype shape, the perfect catenary shape, and we also developed the offset of the bricks through this system. And then really tried to work out how we would build it, so sketches such as this formed a part of the tender package. We brought builders, engineers, and UTS experts to the table to develop the design and do a lot of work, so a lot of hand detailing on our projects that work out exactly how it is to be built. So very large volumes of documentation. And building it was really fun. We wanted to enjoy ourselves in that process. So just a little bit about the construction. We collaborated with UTS. They helped us also to CNC cut all of the plywood panels that we use for the false work. And this is a little bit about cutting them. You can see here that the plywood is notched to receive the purlins, which meant we didn't have to nail those elements together when building the vaulted roof. And then these panels were cut out in the most effective shape, so we're able to get more than one panel out of a sheet, and then nailed together on site, and then formed together and plywood laid across the top to create the shapes. And I'll show you more of that later. But this is the first thing that we made, was a prototype for the project. And you can see the bricklayers here laying the brickwork over the top of the prototype form. And then we put a thin layer of reinforcing over it and then shotcrete the surface. So the prototype had 110 bricks, 60 shotcrete concrete, and when you strip it, this is the formwork shape that we create. We then really started to develop this, and as the project developed, worked on other parts of it as well, and then took that prototype and demolished it and took elements to a UTS lab to check the strength of the binding between the brickwork and between the brickwork to the concrete, so to check that adhesion. It was also useful to demolish the prototype to see how the bricks would perform if we hit it with a large piece of equipment like a front-end loader. And it really performed very well. At the UTS lab, crush testing was done, and this checked the adhesion and the point at which the elements collapsed, and then we felt very comfortable that we would achieve a good strength for the vaulting of the roof. Over the roof form, you can see through here the plywood falsework laid in place and the purlins put in over the top of that. And I'll show you a structure here before we laid the plywood across the top to form the shape that we built the brick vaults from. And then the bricklaying is coming up over here on the real vaults, so these are 4 meters high. And then you can see the bricklayers here working. And then as they build up over to the top of the vaults, you look also, we're starting to prepare the next vault for the building in hammering in the purlins over the top of the CNC cut plywood. And again, it gets sprayed with shotcrete. It's very hard to see in that situation, but sprayed over with concrete. And then later the falsework is removed to reveal beautiful big vaults open to the sky on the roof of the building. And then other elements are introduced into that, such as windows that span to make vertical windows that can take blinds on the future building. The joints between the two vaults are quite critical and are beautifully formed. On the left you can see the layering of the building, so the brickwork, the concrete, and the insulation and plywood that goes over that. And over the top of that, again, we add a standing seam galvanized roof. So you can see through here, the elegance of it is the slimness of the form and the detail that's worked through with the bricklayers and getting the coursing right. One thing you can see on the left-hand side is the bricks are laid with offsets of 50 mil, so you get these 45-degree lines. And all of the bricks are glued together using tile adhesive rather than conventional mortar. On the outside, however, we use conventional mortar, and this is a little bit about how we created the curves for the building.
The purpose of the angle here is to hold the radius of the brick to stop it from slipping. Because it's faced both sides, we can't put a permanent centre in. So we put a radius, a partial radius centre with an arm on it that holds it in place so that we can actually see the lower arris of your bed joint and see the line of your top arris, so you can keep everything straight. But this is the only way we can come up to actually be able to fix it and hold and maintain a face component of the brickwork. Perfect. Okay. Fill in the whole anchor. Completely full. Get some black Sikaflex on the tie. So it's got a seal for the water. And just sink that into the camera blanket.
like so, and then just put a tie in, screw that on. Put a screw, another screw.
And so this is how we form brickwork that's laid pointing down at 40 degrees to the vertical, so almost 45 degrees in that curvature, and then how that integrates with vertical elements at the edge of the building. These are full bricks that are laid, again, at the 45 degree offsets that transition beautifully around corners. The result at Stokes 14 is a very sustainable building that has no air conditioning in the studio space, that has 260 solar panels and makes its own energy. From the street, it presents as a new version of industrial building with its long horizontal slot windows and its steel-framed multi-pane windows. The materials used throughout are very robust, like brickwork, like galvanized finishes. They're not high-spec, but the attention to detail and the ability to make these elements look effortless is where the work was encountered. Coming into the reception space, you experience a low ceiling with prefabricated concrete beams. And then stepping up through the studio, you come into a beautiful light-filled space where there is no air conditioning, models everywhere, drawings pinned on the walls, and an abundance of natural light. And looking back through the studio, you see long desks that are column-free, so we can have multiple people working on each workstation. And then we display our models as our work in progress, but as also as our hero projects that have developed over time in beautiful display cases. Other elements that embody the philosophy of the industrial building, so therefore use lowbrow materials in interesting ways, are the staircase through here. So it's a terrazzo staircase suspended from stainless steel cables. It forms beautiful shapes in the space. And then the meeting rooms have beautiful natural light, ceiling fans, and the materials library is off to the side where we sort and collate new materials. We also have a model making workshop where we make our own models and have a full-time model maker. And at the back of the building we have a canteen that opens onto the beautiful rear lane where other beautiful brick buildings exist, and we feel a part of that family. The laneways are like this, and the windows all open and close automatically. Moving up into the apartment upstairs, there's a steel spiral staircase that sits in a round brick drum. And then this is the final apartment. So you're looking from a small vault to a big vault and then through to the next small vault with offsets in between. It's a beautiful open space and has a very distinctive quality that is different to the main studio space. And customized elements such as a coffee table here, which opens up to have a television inside. And then moving through the space, the shapes of the windows are following the two brick vaults, so it's quite important that the bricks don't distort or change shape over time, otherwise the glass will crack with this detailing that we want to achieve, which looks almost invisible. And there you can see the glass coming to a point, noting that this glass panel is 6.3 by 3.3 meters wide. Artwork is integrated into the only tall joinery elements in the space. And then looking back through the other way, you can see through to an ensuite bathroom off to the side, which looks like this. And then another bathroom in the space that looks like this. A study space through here with another customized piece of furniture, and then looking through to a daybed and library in this area. Abundance of books. And so looking from the outside, you see again those everyday materials, so galvanized roof sheeting and a standing seam, beautifully executed, and then feathering out to a thin edge with no structure. So again, this is a form that doesn't rely on steel to hold it up, and it's just 20 mils of plywood lined with galvanized roof sheeting on both sides. In conclusion, I'd just like to say that this project is the result of huge amounts of collaboration between engineers, consultants, contractors, designers, and we wanted to embark on the project to have a great time and to enjoy the whole process from start to end. And that was achieved through tremendous collaboration and great teamwork. And we had that on this project. So I'd like to thank all of the engineers, the consultants, the collaborators, the designers, the contractors, and the artisans that worked on the project. We had a goal to make it a real pleasure and to achieve something extraordinary. And I feel both of those were achieved. So personally, from me and also from my studio, thank you to everybody who helped us. I'd like to hand now to Brett, who'll introduce the next speaker.
Thank you, William, for your architectural insights. I'd now like to welcome our second guest speaker, Jonathan Lowe. Jonathan has been part of the Northrop team since beginning his career through the undergraduate intern program in 2007. He now manages a team of engineers in the Sydney Structural Group and recently became a principal in the company. Jonathan has led projects across a variety of sectors, with a large focus in the last few years within the education and justice spaces. Communication, responsiveness, and a collaborative approach are consistent drivers in Jonathan's work. He enjoys working closely with clients, architects, builders, and other stakeholders, from project conception through to successful completion. He also contributed his skills and abilities on a secondment in Christchurch following the 2010-2011 earthquakes. Please welcome Jonathan Lowe.
Hi everyone, my name's Jonathan Lowe. I'm a principal structural engineer in our Sydney Northrop office. And today I'm going to be talking about some of the structural challenges we faced on the Stokes Avenue project. I thought I'd take the opportunity to give Northrop engineers a bit of a plug. Not to be confused with the Northrop Grumman engineers. We are a Australian employee-owned company that started in Canberra in 1976. We've got 10 offices across the eastern seaboard, and we're just shy of 400 people. I'm going to preface my presentation with saying that, while I'm here presenting on some of the really interesting engineering challenges, there were a lot of brains involved in this project. Some of them were in Northrop. A lot of them were outside of Northrop. And in fact, some of the biggest challenges that we had on here and some of the best ideas actually came from unexpected places. I reckon I learnt more from the head brickie on this job than I did from anyone else. It was a really complex project with quite a lot of different structural things going on. But for today's presentation, I'm really just going to be concentrating on two aspects, one being the brick arches up in the apartment, and secondly, the brick facade, the curved brick facade. So starting off with the brick arches, I think William covered quite a lot in his presentation to do with the architectural principles, some of the sustainability ideals initiatives that were employed in the project, and a few of the constructability issues. I'm going to take a slightly different approach and talk to you a little about the structural challenges that we have faced, some of the engineering principles, and some of the lessons learnt that I'm going to take forward into future projects. So coming back to some pretty simple structural engineering principles. We've got an arch here, and under gravity loads, an arch works by having all of the elements working in compression. Masonry is a really wonderful material for working in compression, and it actually works remarkably well. As building designers, we start to need to consider some of the other effects on this arch that come into play from the lateral loads, so things like wind and earthquake. As our arch starts to experience some of these lateral loads, we induce bending, and the shell of the arch starts going into flexure. It's kind of our job in this instance to make sure that we've got no net tension in the arch, so there's nothing there to cause a collapse. Kind of taking it to the next step, we've got to look at our arch more globally and see where it sits within the structure. So in our case, the arch was actually sitting up on level 2 of what is essentially a steel framed building. So we needed to consider the additional accelerations that this arch experienced due to the behaviour of the steel frame. Still at this point, we're thinking, yeah, this isn't so bad. We've really just got to make sure that we're keeping all of the elements in compression. One of our original ideas, which came about in the tender design, was to actually post tension and put some pre-compression into the arch using a series of jacks and straps over the top of the arch. By the time we got through to our construction drawings, we actually abandoned this idea and just added some extra self-weight to the arch. Often it's actually the simple ideas that are the best ones. So again, we sort of felt that we were in a pretty good position. Nothing was too complex. But unfortunately, William was selfishly wanting to have some windows in his apartment. So we had to start looking at a few openings in these arches. This slide is showing 4 of the scenarios that we had across the apartment and showing some of the windows that were introduced into the vaults. In some of these, the windows actually range from 900 wide right up to 4.5 meters wide. So in some instances, the ends of the windows were supported by the adjacent piece of arch, which was not too bad. In other instances, we had the end of the window actually supported by a steel plate column, which again started getting a little bit tricky, but it wasn't too bad. In some instances, the end of the window was actually hung from another arch. And in some really interesting instances, the end of the window was actually hung from a slab, which was hung from another slab, which was cantilevering off a 3-story unreinforced masonry cylinder, which was hanging off the hopes and dreams of a structural engineer. At the end of the day, what we found was that this project was one of these projects where a typical detail didn't exist. This is just a picture of, I've quite lazily thrown in one of our structural drawings here, which kind of shows the different scenarios that we were looking at from an analysis point of view. So sometimes we had an arch with an upstand, sometimes we had a very simple arch, then we had the 2 sizes of arches, and then various sizes of windows. This is just a quick diagram to show, where our arch starts to get a little bit more tricky, where some of these reactions are, and how we started thinking about, I actually call this the igloo picture, but just starting to show how the arch started to get a little bit more complex. So we analysed the arches using strand 7, so a finite element package, and we started with the very simple arch, and we started introducing the openings into the arch. With the analysis, we only modelled the concrete shell, which was sitting on the outside of the bricks, and then we added back in the self-weight of the bricks to help with the compression in the arch. This screenshot is from our kind of typical 4-metre high arch with the opening cut out of it. We then started introducing a little bit more complexity into the models to analyse how the loads and the stresses kind of navigated their way around the window openings. The photo on the right is actually the little wedge shape at the right-hand end of that window, and you can kind of see the reinforcement that goes over the window hood. But this is before they've added the reinforcement for the wedge-shaped triangular concrete column down the side. Now, I think William's already mentioned the prototype arch that we built down on the ground floor of the existing building. And from my perspective, this was probably the most important thing that we did as a design team and as a construction team for this project. There were a few people that sort of had a half idea about how they might build it, but this was really a testing ground for some of the finer points. How do we build the arch? How do we build the false work for the arch? how do we remove the falsework from the arch? And then even some of the more basic things from the subby's point of view. So how are we actually going to shotcrete this? How are we going to finish the concrete? And the list goes on. So we really learnt a lot from this prototype, and I think, at least for myself, it gave me a lot more confidence in the build quality and also the robustness of the structure itself. There was a few photos in William's presentation around the demolition of this prototype, and from the builder's point of view, it actually took a lot to knock it over. So I've thrown this photo in, apart from it being me in a pre-COVID body. I just wanted to give everyone an appreciation of the falsework system. Quite a lot of engineering went into the falsework system itself. The site foreman, Toby, he actually had a bit of a past in boat building, and I think that kind of shines through in how the falsework system goes together. There's a lot of considerations around, okay, how much workspace do we need under so we can continue with the build? And then, as William mentioned, this was actually, UTS really helped us out here with CNC cutting of all the falsework plywood. So the traditional brick arch, as most people know it, is obviously working in compression. And for a typical arch, this would involve mortar joints between each of the bricks. One of the challenges that William threw at us during the design phase was that he didn't want to have mortar joints. He wanted to have a dry stacked arch where the bricks were just face to face. So, after losing a few nights sleep over this and having to think about how can we actually get this thing to stay together, we started throwing around some ideas around mechanically fixing each of the bricks to the concrete shell, and then also thinking about the bond between the bricks and the concrete shell. The picture on the left there is the head brickie, Gareth, kind of placing one of the bricks in, and it was actually his idea to come up. It was his idea that to use tile glue between the bricks. So he actually was using tile glue within the frog of the brick. And for anyone who doesn't know what a frog is, the frog is that divot in the top of the brick, which when you've got mortar in there, actually gives you that interlock between the adjacent bricks. And actually that was one of the really genius ideas. It actually solved quite a few problems for us. One of the other things I'll mention there, and anyone who's worked with William would know this, he never leaves anything to chance. So the brick pattern, as it went over the arch, it was a 50mm offset for each of the bricks, and that pattern actually went up over the crown of the arch and right back down the other side. The challenge that we had was that as it was being built from either side, not from one side over, we had to make sure that that pattern was going to meet up correctly at the crown of the arch. So we noticed that having had a look at a sample of the bricks, it kind of varied up to 2 to 3 millimeters in the height of the bricks, so that the bricks started to wander over the course of 10 courses of brick. So on the falsework system, we actually had every brick course marked out, which gave the brickies an opportunity to shave down bricks every few courses just to make sure that we were still on track. Here's a great shot of the shotcreters working on the prototype. This was an interesting one, but they had to work out how they were going to actually spray this thing. So on one side of the arch, they sprayed top to bottom, and on the other side of the arch, they sprayed bottom to top, just to see how it was going to work and how they were going to finish it. They also mucked around with a few different mixes to see, what was going to be the easiest to finish. So on the prototype arch, we actually built a one-to-one scale model of the smaller arch, which is about 2.8 meters tall. And on that model, we used a 110 brick and a 65mm concrete shell over the top. The reason we did that was to effectively scale down the slenderness of the larger, of the concrete shell for the larger arch. So on the larger arch, we flipped it around and we actually used a 65mm brick and a 110 concrete shell. But in this photo, you can see that to give that illusion of having a really thin concrete shell and the normal 110 brick, we actually used 110 bricks right on the ends of each of the arches. Here's a screen grab. Again, I've kind of been lazy and thrown in one of the structural drawings, but of the details from our tender set. So when we produced the tender set, this was obviously before we'd done the prototype, we were quite concerned about how the bricks at the crown of the arch were going to perform. So we'd actually specified that everything across the crown of the arch was mechanically fixed. After we'd done some of that testing, and we'd, I guess, given ourselves some comfort around how the bond between the brick and the concrete was, we actually backed that off and decided we would only fix 1 in 3 of the bricks, mechanically fix 1 in 3 of the bricks. So that's what you can see on the photo on the right. You can see the stainless steel pins in those kind of diagonal patterns. So we've kind of built the prototype now. And once the builders and their subbies had a chance to learn a few things on how they were actually going to build it, it was out, we set about trying to learn a little bit about how it was going to behave in situ. So this photo is a picture of one of my soon to be retired, but probably will never retire guys, Brian Wood, testing out the bond strength between the bricks and the concrete. And we basically got out there one afternoon with a cold chisel and a hammer and just went about trying to destroy this thing. I guess the purpose of this was to really gain a bit of insight into the bond strength between the bricks and the concrete, and also how the bricks and the bricks using that tile glue. Qualitatively, we actually kind of found these bricks to be quite chalky. Like if you really gave it some, you could crack these bricks in half with your hands. So we found that the bond strength between the concrete and the brick was actually stronger than the brick itself. I guess on top of the very qualitative testing that we did on site, we wanted to get a little bit more data on how this thing was going to perform. So we had been working with the architectural school at UTS, and then after that the engineering school at UTS, and kind of talking about a few different ways that we could test out the prototype. We found a few standardized tests through ASTM and decided that we would conduct some 3-point flexural tests with the lab at UTS. So basically we got these samples taken down to UTS. I think there were 3 samples. They each weighed about 120 kilos, and using their 200-ton machine, we carried out these 3-point flexural tests. The team down there at UTS came out with some really uninspiring graphs for us to look at, and we kind of back calculated the flexural strength of the concrete shell to be about 50% more than what we'd theoretically worked out. So that kind of really gave us a lot of comfort around how these things were going to perform, and it was probably quite indicative of how difficult the prototype was to demolish. So that's just a shot of the test lab down at the UTS test lab down at Botany. I thought I would show this photo just to kind of talk to some of the subtleties of the design and some of the challenges that actually brought up. So this is a photo of I guess you come to the top of the stairs and there's a window with some brickwork below it. So to any normal person, the sensible thing to do here would just be to bring that vertical brickwork down to the slab. But to a perfectionist like William, he didn't like the interface between the adjacent arch and that vertical brickwork. So what we've got here is actually vertical brickwork supported on 7 courses of bricks that are following the parabolic shape. This was quite a pain at the time, but in hindsight, it's actually one of my favourite details of the project, particularly because as it comes around to the top of the stairs, it actually curves into the big cylinder that forms the stair core. So this is just another shot of that area. And as you can see, kind of the parabolic curve of the arch kind of just follows straight into the top of the stair core and then wraps around into that cylinder. So it's subtle, but it's pretty wild. This is another shot of, so we were dealing with parabolic arches. We're also dealing with some flat sophites. So this is a kind of picture of the library study up one end of the building. And you can see it's a flat brick ceiling. In this instance, we actually use mechanical fixings, a false work system, mechanical fixings, and then poured the slab over the top. It looks fantastic. The photo on the right is the flat ceiling over the stair cylinder. So that's it for the arches. I'm going to talk a little bit about the curved facades. So this is a picture, this is one of our structural drawings, just kind of showing a couple of the different scenarios we had for the facade. There was basically 4 scenarios. This one is where the top of the brickwork kind of curls out away from the facade. And you can kind of see that in the photo on the right, just the secondary steelwork and the galvanized steel sheet. The next scenario was what we called the little half crescent moon, and then the skirt where it kind of peeled away from the building at the lower end. For all of these, we designed a secondary steel structure that came off the primary columns, and then between the columns, we had this secondary structure that was kind of really picking up a fair bit of torsion due to the eccentricity of the brick weight. A couple more photos here. This kind of shows the skirt detail of where the bricks are kind of peeling away from the building. This was probably the simplest version, obviously because you've got the bricks kind of supporting themselves in this with an angle at the base. The other interesting part about this detail was how that bottom course of bricks, which was underslung to the steelwork, was connected. We kind of tossed around a few different ideas here, and in the end we landed on using a stainless steel, basically making up modules of bricks, I think 8 bricks at a time, using a stainless steel dowel, and then lifting that up and securing it to the underside. These are just a couple of photos of the galvanized sheet that was affixed to the secondary steelwork before and after the bricks went on. And as you can see, I mean, the brickies on this job were absolute masters. Once you kind of got about 2/3 of the way up that crescent and it started peeling away, there are mechanical fixings back to the steelwork. So I guess to wrap up, I just wanted to go through my 3 takeaways that I've got from this project. First one, and this is not what a structural engineer would normally say, but it's okay to not know what you're going to do at the start of a project. We started working on this project. It was really not clear to us how we were going to design, let alone build some of the elements on Stokes Avenue. And despite enormously underpricing the job through not understanding the complexity of it, it was a really great example of a project where we're kind of learning from each other on the way through, and learning from the people, the whole team. Second takeaway is that good ideas come from around the table. Like I was saying earlier, I actually think some of the best ideas came from the subbies and the guys who are building this. I've almost no doubt that a structural engineer would never have proposed to use tile glue to solve a structural problem. But as soon as Gareth had put it out there and we talked about it, we realized it actually solved several problems, buildability problems, structural issues, and it really moved the project along. I guess the thing there is you need to leave your ego at home and just go into these things with a really open mind. Third thing is collaboration. Without collaboration on this, we would have really struggled to get to where we did at the end of the day. Again, going into these things with an open mind, listening to people was absolutely key to getting the result that we did. So that's it for my presentation. Just to finish up, I'm going to throw back to Brett to wrap up the evening. Thanks.
Thank you, Jonathan, for your engineering insights. Now that's all we have time for tonight, so please join me once again in thanking William Smart and Jonathan Lowe for their time and insights shared during tonight's presentations. I'd also like to thank Engineers Australia for helping make tonight's webinar possible. Now we'd appreciate your feedback on the program today to help us improve and plan for future sessions. So please complete a short feedback form which is linked in the description box below. Thank you again for joining us, and we hope to see you at our next webinar. Thank you.